So today there are two parts of the test. So we talked about parametric estimators, or parametric function approximators, not estimators. Non-parametric function approximators. So we talked about parametric function approximators in the previous class. I wanted to remind you of the setting. So the setting is I have bunch of points xi, yi, I equals 1 to, I don't know, maybe capital N, and this is Rn cross Rn. So either we are trying to store a value function at specific x, or we are trying to store policy. So this could be the state, this could be action, or this could be state, and this could be the value at that particular state. You can also use it for model approximation. So this is your x comma u, and this is your f of x comma u. And then you can use it for cost function approximation. So this is x comma u, and this is c of x comma u. Okay. So in the parametric case, we talked about basis function, we talked about neural network, we talked about RKHS, and then we talked about decision tree, decision/regression tree. Okay, so let's talk about the non-parametric case today. So the first one is local averaging. So the idea in local averaging is that you have a space let me draw, this is my Rn, this is my Rm, and so I have a point here x1, y1, x2, y2, x3, y3, and so on. And so we know x1 maps to y1, x3 maps to y3, x2 maps to y2. And I want to estimate the function at a point x. And I don't want to use any of this parametric method. So in parametric method, there is a parameter, and then you need to estimate that parameter by solving a least square problem, as we had discussed in the previous class. In the non-parametric case, I don't want to estimate anything. I just want to directly find out, or at least come up with a value of x. I don't want to find out what theta is. So if that is the constraint under which we are working, what could be a reasonable way to estimate the value at x without appealing to any parameter? So no basis function, no neural network, no RKHS, no regression tree. Yes?
Nearest neighbor.
Nearest neighbor. So you will pick 2 or 3 nearest neighbors to x. So well, there are only 3 neighbors, so let me add 4. Okay, so I'm going to pick 2 or 3 neighbors of x, nearest neighbors of x, and then I can take the average of the values, and I can find out what the function value f of x looks like. So nearest neighbor is another technique, so that will be number 2, but that's definitely one of the ways by which we can estimate the value of x. So the 3 nearest neighbors to x are x6, x2, and x4. So I'm going to pick y2, y4, and y6. Y2, y4, y6, I'm going to average them. I will take the average of these 3 values, these 3 vectors, and I'm going to say that my function value at x is equal to the average of these 3 values. So that's roughly what local averaging tries to do. Okay, so what we will do in the local averaging, so one of the algorithms would be I'm going to divide the space Rn union of maybe I equals 1 to p xp. So I'm going to define, well, sets xp. Each of these are mutually disjoint sets. So xp are all disjoint. I'm going to find, so given x, let xp naught be the set such that x is in xp0, and then I'm going to define the set yp as the set yi such that xi is in xp. So these are all the yi's for which xi is in this set xp, and I'm going to define the function at x as average yp0. So this would be my x1, this would be my x2, this is my x3, this is my x4, and this is my x5. Okay. So I have this space Rn. I'm going to partition it. So this is known as the partitioning the space. So these are all disjoint subsets of the space Rn. So I partition Rn into 5 disjoint subsets, and then I'm going to define y of p as the set of yi such that xi lies in xp. So I'll collect all the x in this x1, and I'm going to call it y1 on this side. So y1 is, we have x2 and x6 in x1. So y2 and y6. So this is my y1. These 2 points, only these 2 points are in y1, okay? Not the rest of the space. So rest of the space is not part of y1. And then I have x2, it contains x1. So this would be my y2. And then x4 contains x3, x5, x4. So y3, y5, and y4. So this is my y3, no, y4. And my y3 and y5 is going to be empty because I don't have any points in x3 and x5. So I don't know what y3 and, sorry, the capital Y3 and capital Y5 is going to look like. Okay, so this is a local averaging approach. You partition the space, you look at the y's, corresponding y's, and then you take the average of those y's, and that gives you a function approximator. Okay, any question? Yeah.
Going through, first we divide the space into based on a single point, and then we.
No, we are not dividing the space based on single points. Like we can divide the space as you want. So like we were talking about the inventory problem, right, in the previous class. So we said there is low inventory, medium inventory, and high inventory, right? So let's say low is less than 10 items, medium is 10 to 50 items, and high is 50 plus items. So then you have partitioned the space into 3 separate sets. Now if you know if your x lies in 1 to 10, then you pick the corresponding y's that you have and you take the average of those y's. Yeah.
And yp is the average of all
yp is not the average. Yp is the set of all y such that xi belongs to xp. Xp naught is used when I'm trying to, given x, I'm trying to estimate what the function value looks like. Okay, that's average of yp naught. Any other question?
But there are many x in xp.
That's right.
So the average of yp is mean to which xp?
No. You pick. So I have picked x1. So I have picked here x1 as my. So x1 is my partition. So I pick a point x. Now x belongs to x1. x1 contains x6 and y2. So I'm going to define my f hat of x as y2 plus y6 over 2, because that's what the average of y2 and y6 looks like.
So we can see all of the x in this area xp be y2 plus y6 over 2.
Yes.
So all of the x.
Yeah, whatever x's belongs to this x1 set, you can take the average of all those corresponding y's. Okay. So that's a non-parametric estimator because we are not using any parameters to deduce the function. Yeah.
What if x is in x5?
Then you will not be able to come up with an appropriate value of f hat, and so you can either set it to be infinity or you can set it 0, but that's a convention. And sometimes when you create these conventions and you put it in production, you might have issues further down the line. So whenever you are trying to create these conventions in a production system, you have to be very careful so that it should not be construed in the future as. So for instance, if your convention is that, okay, if x5 is empty, then f at x is going to become 0, then later on downstream, some other developer comes downstream, and then that developer would think, okay, if f at x is 0, then it means it's 0. But the point is you had made a convention early on, and you have not communicated that convention to downstream people, and that kind of happens quite a lot. Okay, so you have to be careful when you make such conventions.
So how do you pick those bets, x1, x2, and 3?
It's all dependent on your problem statement. Like in inventory problem that we were talking about in the previous class,
So
you have low, medium, high inventory.
So it's like take it randomly or have a specific strategy?
It all depends on the application. So you can't have for an inventory control, you can't have a randomly picked state like the partition. It's much easier to communicate and to code low, medium, high than to try to come up with a very random space and then do it that way. But if you're dealing with, say, very high dimensional data, you're doing something like a million dimensional image, then you can do a random projection and then you can use like a smaller dimension x to do the partitioning. So that's also something that you can do, but that's for high dimensional spaces where the partition is not very clear how the partitioning is supposed to be done. So then you do it via projection onto a lower dimensional subspace. Okay. Okay, is this idea of local averaging clear? And then the second one, which we already discussed, is k nearest neighbor. So the problem with this, as we pointed out, I mean all of us have discussed, these are empty sets. So then I can't really define f hat of empty set because the x belongs to a set where I don't have any data points. So in that case, what you do is you pick k nearest neighbor. So that way you can, that way you know that you will never have an empty set, right? Because it's like 5 or 6 or 10 or 15, whatever that k is. You pick the nearest neighbors and then you average those values. So this would be, let's say, given x, find k nearest neighbors. Let me call this, what should I call this? Nn of x, which is a subset of Rn. and then you define y of x, which is the set of yi such that xi belongs to nn of x. Maybe I'll put a k here because this depends on the value of k you pick. And then your f hat of x is equal to average y of x. So this one doesn't, this one gets over the problem that you have in this particular case. But then the problem there is if your x is too far off from all the neighbors, then what exactly are you computing? Then your function is, it gives you a number, but you don't quite know whether it's a good number or a bad number. But it gets around the difficulty here. So take it with a grain of salt. Any other question? So k nearest neighbor is a very difficult function approximator because you see the problem is how do you do differentiation in this case or how do you do differentiation in this case, right? So we are, if you think about it from the point of view of optimization, the value function needs to be differentiated because we are trying to do the optimization, but policy doesn't need to be differentiated. We never differentiate the policy in the context of optimization. As a result of which, these are very good function approximators for policies, but may not be as good function approximators for value function. Which is not to say that people have not used it for value function approximation. It's just that you won't be able to then do differentiation. So then you will have to come up with optimization for non-differentiable functions, and then you will have to figure out some way to do the optimization in that case. Yeah.
I was going to ask then, what's a practical use of k nearest neighbors?
I mean, just for function approximation.
Like, maybe like an example.
Like an example, okay. Let me think. So let's say you are in a ride-sharing setting and you need to assign a driver to a rider, okay, and your policy said, so you did some optimization. I mean, we have written papers on it and there are many papers written on it. So you did an optimization and you said, okay, if this is my xi, if this is where the driver is and if this is where the driver is and if this is where the rider is, then you randomly pick one of the drivers and assign it to the rider. Now the driver is here. It's neither here nor there. The driver is here. So how do you assign the rider to the driver? Well, you look at the k nearest neighbors and whatever that policy said, you basically assign that driver in that particular fashion. Okay, so in that particular situation, it's a very natural way to apply k nearest neighbor as far as policy is concerned. So assignment is a policy, but how the value function is going to look like, I don't think this would be a good way to approximate the value function. Okay. But that's just one example.
Yeah, I love that example.
Oh, good. I did my job. Okay. Anyway, so k nearest neighbor. So if you think about it, this is also a problem where if the driver is too far off, should you do the assignment or should you not do the assignment? So I don't know. Like I have been in a situation where the Uber is like, I don't know, 30 minutes away, and I hated that experience, but at least I got a cab, you know. So, anyways. Then the third one is another kernel method, but different from RKHS. Can I erase this side of the board? Okay. Nadaraya Watson kernel, and here your f hat of x is summation k of x xi yi over summation of kx xi. I goes from 1 to n, I goes from 1 to n. Remember, we have n data points, so I'm taking the weighted average, and this k is known as the kernel function, which is different from the kernel used in RKHS, and k of x comma y. Well, I've already used y, so I guess I cannot use y. X comma I don't know, x bar, okay, could be exponential x minus x bar over 2 sigma square. It could be exponential of x transpose x bar. It could be exponential of and so on. Once again, we are not using any parameters. Well, kind of, sort of, we are using sigma as a parameter here. Okay, but you kind of pick a sigma and then you live your life forever with that sigma. You don't try to optimize sigma. But I optimize sigma, but I'm basically not doing the right thing by optimizing sigma. So you essentially pick a sigma and then you do this way of averaging, and you get a value of f hat of x. That's called Nadaraya-Watson kernel. Some people have written papers about how transformers are an instantiation of this kernel method applied on top of neural network. So I went down the rabbit hole yesterday, and then I realized I can't teach it in the class, so I'll just skip it. But basically, they pick this kernel function, and they pick a bunch of neural networks, and then they are trying to, the neural networks gives you the yi, and then you use this particular kernel function to come up with f hat of x. There is something like that happening in the transformer network. We'll talk more about it in the reinforcement learning class next academic year, but yeah.
Is that like the equating x transpose x bar and that yi is like the value function? Value?
Kind of, sort of. In the transformer case, that's exactly what is happening. Okay? So this yi itself comes from a neural network, and then this one is basically this, I don't know what you call it, query transpose.
So that would basically make up the attention map, I guess.
Exactly. So that's what is happening. And then you can put like a bunch of vectors and matrices and all that stuff here to make it more cool, but that's the underlying idea. And then the fourth one is, no, third one is spline interpolation. So we talked about the interpolation thing, like you have the value function at these points, and then you can do the interpolation like this. So spline interpolation takes it a step forward, and now you can do polynomial interpolation between different points. So that's called spline interpolation. I can't write the expression because it's too difficult. But there are spline. So linear interpolation is a very simple spline method, and then you can make more complicated splines based on polynomial interpolation. And if you have looked at 3D graphics, they also use some sort of interpolation to, I don't know, make movies. Like if a tiger is speaking something, then basically they are using some sort of interpolation technique to show how the tiger's mouth is moving and all that stuff. So a lot of the early work was in spline interpolation, and then it kind of grew from there. I have not seen anyone using spline interpolation in the context of approximate dynamic program, because this is a very computationally heavy activity. But it does give you very nice differentiable map. So if you're looking for a differentiable map, spline interpolation is the way to go. It seems to me that this is also going to be differentiable, but the derivative is going to be quite complicated because each of these are differentiable maps. So you can actually differentiate this with respect to x. I just feel that the derivative will be really horrible, so probably not a good idea to differentiate it. Yeah.
Number 2 here, is this neural network?
Which one?
Number 2, under this parametric.
This parametric, yeah, this is neural network.
Okay, each of these are under the neural network.
Sorry?
These ones you are mentioning now.
No, it's not neural network. No, neural network, we talked about it in the previous class. Okay? All of this stuff is recall from the previous class. This is the non-parametric stuff that we are doing in this class. Okay. Any questions on the non-parametric? That's all I have on the non-parametric side. Just trying to collect all the ideas together.
What's the name of non-parametric? What's that coming from?
Because there are no parameters involved. Remember, in the parametric case, we had theta,
Oh, okay.
right? We don't have any theta anywhere. Okay? That's why it's non-parametric. There is no theta to optimize. There is no optimization whatsoever.
So there's no like hyperparameters?
No hyperparameter, nothing. This is just what it is.
What's
Okay.
the meaning of the sigma?
Sigma is a hyperparameter, but you don't really optimize it. You just pick a sigma and then you live your life.
How do you know the sigma is optimal sigma?
You don't. You just keep doing trial and error and you figure out some sigma that works well for your problem.
Why is sigma not the standard deviation for x?
See, the thing is that all of these methods are applicable for very high dimensional spaces as well. So if you have a 1,000 dimensional x, this one will work in 1,000 dimensional x as well. But then when you talk about standard deviation, what do you mean by standard deviation in a 1,000 dimensional thing? Because you get a matrix, you get a covariance matrix. That covariance matrix is going to be a 1,000 cross 1,000 matrix. What do you mean by sigma in that particular space? There is no sigma. There is sigma 1,1, sigma 1,2, sigma 1,3, and then there is a whole bunch of sigmas. So then you can pick sigma as trace of your covariance matrix, but then trace, I don't know how good of a function approximator that's going to give you. So there is a lot of dark magic that you have to do to make things work. Any other question? Okay. So we did parametric, we did non-parametric. Now I want to do random function approximator, which we alluded to in the previous class. So the first one is random kitchen sink. Don't ask me why it's called kitchen sink, but that's what it's called. It was published in NeurIPS, I think, in 2008, and then it got Test of the Time award in 2018. So it's a very famous paper. And here you pick your f hat of x. Let me write it as f theta of x. Is summation theta I phi I of x. I goes from 1 to n. But phi I of x is actually cos of omega I transpose x plus bi, or it could be sine of xk minus ti, or it could be indicator function of x is in bi, where all of these are kind of randomly picked. So omega is randomly picked, b is randomly picked, ti is randomly picked, k is randomly picked, this bi is randomly picked. So you can pick these values randomly The only problem with this random thing is that if you were to start a neural network, you can have 100 parameters, but if you use these random things, then you will have to have 10,000 parameters. Okay, so that's the only shortcoming. But the benefit is you can just do a direct regression. It's a linear regression problem in theta I, so it becomes much easier to solve the problem. But the capital N is much, much larger in this case in comparison to any of the parametric methods that we have talked about. Okay, so this is known as a random kitchen sink. So K is uniform, Ti is IID, omega I is IID, Bi is IID. Maybe this is coming from a Gaussian distribution. And this Bi is basically a grid, a square, but or a cuboid, but the vertices of the cuboids are picked randomly. So that's this function approximator. The second one is called bootstrap aggregation. In short, bagging. So this B and this AGG. So one thing you should know, if you want to do well in machine learning, you need to become a person who can come up with cool names. Okay? So bootstrapping was an old technique. Aggregation was even older technique. So somebody came up with bootstrap aggregator and then gave it a name, bagging. Okay? So all over the machine learning literature or reinforcement learning literature, one of the critical skill set is you should be able to come up with cool names. Okay? Period. And if you can't come up with cool names, you have to partner with someone who can come up with cool names. And I'm not that partner. Okay? I can't come up with cool names. I have tried and I have failed. Okay, so I have a data set D, which is xi, yi, I equals 1 to n. I am going to, I have used I, so I can't use I now. So I'll use P. P equals 1 to capital P dp. So I'm going to take IID samples from this data set and create another data set dp, which is picked IID from this particular data set. And I have capital P such data sets. Now each of this I can train, I can take dp as an input. I can use a parametric function approximator. And I can come up with f theta p, which is so I can come up with, I can use this data set to come up with a function f of theta p. And then I'm going to define my f of x as summation wp f of theta p x. P equals 1 to capital P. And then I can optimize the wp using some sort of linear regression problem. So there are two times when you are doing regression here. The first time you are doing regression, for every p, you're running this parametric function approximation regression and you're getting an f theta p. So let's say I have 1,000,000 points. I separate them into 20 different subsets. Now I have 20 such neural networks that I have trained based on each of these data sets. I have 20 neural networks. Now I'll pick all those 20 neural networks, come up with an appropriate weight through another regression problem, and that will be my function estimate. Yes?
So is that just to say that there's no remaining entries missing from capital D?
Yeah, this is an equality, but you can have duplication. You can have x1, y1, it could be in d1, d5, and d10.
Okay.
So there is duplication. There is a possibility of doing duplication. Okay, and then you get this function, and then you take the weighted sum of the functions. So this is known as bagging. And then the third one is random forest. which again I had alluded to in the previous class. So one of the problem in getting trees, so if you want to come up with one tree, it will be a very long tree. Okay, x1 less than 5, x2 greater than 5, and you keep putting all those constraints, and lo and behold, you have like thousands of leaves in your tree. So the idea in 2000, early 2000 was, why to just focus on one tree, just create a forest. Sounds so natural, right? So we don't want one tree, we want thousands of trees. So thousands of trees is known as forest. So that's why it's called a random forest. Now what is random about it? So remember in the tree structure, so if you go back to 1970s or 80s, there is an algorithm to come up with a tree from data. Okay, and that algorithm is very complicated and very time consuming. So you cannot really, for high dimensional problem, you cannot really come up with a tree. For small dimension, it's very easy to come up with a tree, but for high dimensional, it is difficult. So how do you come up with a tree? Well, I need to pick what is the xk here, and then what is your xk prime here. So I'm going to pick xk randomly, and then I'm going to figure out the threshold. And so on. So I'm going to figure out the threshold using some optimization algorithm. And once I create this tree structure, then let me call this f1 of, so f hat 1 of x. Now I'll create, so I've created this tree, and I've picked k and k prime randomly. So I picked some random element here and I did the splitting, and then I picked another random element here and I did the splitting. When I'm splitting, I'm figuring out this alpha through an optimization algorithm. Now I've created the first tree. Now I need to create the second tree. So I'm going to pick the data set xi, yi minus f hat 1 xi. Now this is my new data set, 1 to capital N. Okay, so I've constructed a new data set, and now I'm going to send it to a random tree creator, and then it will create this random tree. And then I'll take another residual. So this is known as residual. So I'll get the residual again, and then I'll create another random tree, and I can keep creating trees, so on and so forth, in order to get a forest. Okay, and that forest will become my function approximator. So the forest is going to look like summation f hat kx, k goes from 1 to capital K. So you can run it, you can create thousands of trees or tens of thousands of trees, and then you can create your function approximator. And this algorithm, random forest, is actually extremely fast. So even if you have a 1000-dimensional x, what you get is non-differentiable function. But if you have 1000-dimensional x and 1000-dimensional, not 1000, but whatever, some 5 or 10 or 20-dimensional y, you can actually create this random forest in a matter of a couple of minutes on a regular computer. Yeah.
So how can we show the alpha and beta in the tree?
There is a very complicated optimization algorithm for figuring out alpha and beta. So you can of course pick it randomly, but you can also pick it in a more easier fashion, but it requires solving an optimization problem.
Typical like machine approach for that is you can just use a scheduler and have it try different combinations of
That's exactly what this algorithm is trying to do. Okay. Any other question? Okay. So that completes our discussion on function yeah. Because this xk is picked randomly. This is picked randomly, this is picked randomly. What values will come here is picked randomly. The only thing non-random about is picking of alpha and betas, this threshold. But other than that, all of this is quite random.
So what about
this function. Yeah, so this function is basically, so if you have f of x and let's say this is 5, 6, 7, 8, that's the value at the leaf, then f hat 1 of x will basically say if xk is less than alpha and xk prime is less than beta, then it's 5. So you can think of it as 5 if something 6, if something 7, and so on. Okay, so that's your function f hat 1 of x, and f hat 2 of x is also going to look like this, f hat 3 of x is also going to look like this, and that creates your approximate. So in the context of approximate dynamic programming, we always want a differentiable value function. So people generally pick parametric function approximator for value function. However, if you are a PhD student and you want to prove theorems, then you can pick non-parametric function approximators because those have some desirable properties. On the other hand, when you are looking at a policy, I think it's much more, it's okay to use these bagging or random forest to do the policy approximator, purely because you don't quite require it to be differentiable. So cost function, model, and value function, you need to be able to differentiate it. Policy, you generally don't need to differentiate it. So policy, you can use any function approximator. But for value function, for model, and for cost, it's always good to use a differentiable function approximator. And that's pretty much it for function approximation. So we'll go into more depth. So I've given you an overview of different function approximators. It took me, I think, 6 months to figure out this list because everything is all over the place in this area. But finally, now I have a list, so I teach it in all my approximate dynamic programming class. I've taught it in reinforcement learning before, I'm teaching it again. And then next year I'll teach reinforcement learning and I'll teach all of this again. But in the reinforcement learning class, because it's a 7,000 level class, I will make it more concrete and more complicated by proving what this function f tends to satisfy. Like for instance, one of the elements that we talked about in the previous class is neural networks and RKHS. They are universal function approximators for continuous and bounded functions. So what exactly does it mean for something to be a universal function approximator for continuous and bounded function? So we talk a little bit more about it in depth in the reinforcement learning class. So that's pretty much it. I think we are done with the entire material that we wanted to cover in the course. In Monday's class, by popular opinion, I'm supposed to teach how to solve an optimization problem. So given an optimization problem, how do I figure out what's the right algorithm or mix of algorithms to solve it? So I'll go over it mostly based on my own experience of solving optimization problems. So there is no book, no chapter, no written material, nothing from which I will be able to prepare that lecture. So I'll do it over the weekend. I'll think about what's my own mental model of solving an optimization problem is. And then I'll try to explain that in the class through several examples. So the examples that I've worked on are ride-sharing systems, pricing algorithms. I've worked on EV charging systems. Yeah, and maybe a few more. And I've written a lot of theoretical papers in reinforcement learning. So I'll collect all of those thoughts and I'll then prepare for the lecture. But don't keep your hopes high for Monday's lecture, okay? It could be a disaster. So just come with very low expectations. And so anything above that lower expectation is going to be a benefit of coming to the class. So thank you so much. See you on Monday.